Hello and welcome to another video. In this video we're going to be working on minimum obstacle removal through each corner. And I was actually going to record this one live, but then I did the non-optimal solution live, so I didn't want to take it too long, so instead I'll just do a review video instead. So in this one you have a grid, and every cell has an empty cell or an obstacle, and you can move in any direction and return the minimum number of obstacles to remove such that you can go from the upper left to the lower right. Yeah. And so I'd say this problem is definitely more like a medium, especially to get a solution that's like reasonable. I mean, optimal is still not that bad, to be honest. But essentially, here we can basically get rid of, like, we have to get rid of this guy. Actually, we don't have to, right? So there's a bunch of things we can do. So we can go like this. That's 2. We can go like this. That's 2. Go like this, and so on. And then this, there's just already a path. So the main thing to recognize here, to make the problem pretty simple, is we just have a cost of going to a cell. And if the cell is empty, that cost is 0. And if it's a brick or obstacle or whatever, that cost is 1. And so that's all we have to do. So we can just do like a shortest path, and the cost of going to a brick is 1 and empty is 0, and we just do a shortest path from here to here. So for example, if we take a path like this, we go to 1, 2, 3 bricks, so that this path removes 3 bricks, so that path is length 3. And then that's basically it. So this would give you, so if you use Dijkstra's and you literally just do this with a heap, and then anytime you're calculating distance, you just check, like, am I going to an empty cell? If that's the case, then I keep the same distance it currently took. And if I go to a brick, then I add 1. That will give you a solution. That's the one I came up with originally. But there's a better one, and I was thinking about it, and the reason that it works is because the cost of going into an empty cell is 0. So normally you kind of have two paths, like I was showing before, where you have, like, is your edge weighted or not, right? So if it's weighted, then you use Dijkstra's. And if it's unweighted, where every edge is the same, then you use BFS. Here we kind of have we have one edge that's 1, and then we have one edge that's 0. So if you think about it, what we can do is, like, the distance to go to some square and adding to that path. So, like, let's say we go from here to here. This has some distance d. As long as from this square we don't go to another brick, right? Like we get to take this path. This is the same exact distance. So we can use that by using a BFS, where we basically have two conditions now, same as before. Do we have a brick or not? And if we don't have a brick, like normally in a BFS, you add things to the end of the queue and you increment the distance. Well, here we can just keep adding to the front, because it takes the same distance to go to an empty cell as to another empty cell that you can get to that cell by not going through any bricks, right? This is the same. So, like, if I go here in, D time, then this is D, this is D, this is D, this is D, and so on. And so we can use that. So we can basically do a modified BFS where when we look at child, like, nodes, or not child nodes, but like other nodes we can go to, we're basically going to have a queue, and we're going to pop a node, and then if the next node we're going to is a 0 or like empty, we can append to the front of the queue. And if it's a brick, then we'll append to the back. That way, whenever we go to a cell, and it makes sense, right? Whenever we go to a cell with some distance and we pop, any neighbor that we can get to, or any node we can get to from that node without going to any bricks, should be popped before all the other nodes, essentially. Because all of those neighbors have the same distance. So, like, to demonstrate this, I guess we can basically say, like, let's look at let's look at this example, I guess. So let's just, like, for this grid, let's just, like, number the cells so we don't have to have, like, an X and Y coordinate. So let's say this is cell 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're trying to go from 0 to 14. So essentially, in our BFS, we're let's probably make this, like, smaller and stuff. Get rid of, do a BFS up here. So in our BFS, we're just going to have like distance 0. So our, we're going to have an XY coordinate, but let's say for this case, we just have a distance and the cell number as our example here. So here we're going to have distance 0, cell number 0, right? And then we're going to pop this cell and we're going to look at all of its neighbors. And so this neighbor also is empty. So this neighbor should go to the front of the queue. So we're done with this. Now, I guess, yeah, let's actually use another color. So we're done with this. Now we're going to check the neighbors here and here. This neighbor should go to the front. This neighbor should go to the back. So now our queue would be 0, 5, and also 1, 1, right? Because this neighbor has a brick, so we're going to add 1 to the distance. So then we're going to pop this guy first. So we're going to pop this guy first. Yeah. Okay. And get rid of that. And then we're going to go to that cell's neighbors, which are these two. Brick, not brick. Brick we add to the back because the brick should go after everything else we have. So brick we're going to add here. This will be distance 1, cell 6. And non-brick we're going to add to the front because that should be processed before everything else because it's also empty. Essentially, you're basically saying like process everything. You can even do this in a while loop. You can say like process every node that this node is connected to that's not a brick first, and then, or you could have like 2 queues or something. But the best way is just put everything that's empty in the front. So essentially from here, we're going to go to node 10 with distance 0 and this node. And that'll process that. Then we're going to pop this node 10 and we're going to go to its neighbor. So that'll be node 11. So we're going to put node 11 up here with distance 0. And this is basically going to keep happening. So essentially, we're just going to keep popping off the front things that are distance 0. And then eventually, and we're going to add these bricks to the end. And eventually, we're basically going to go through all of this before going through anything with bricks. So we'll basically never get to any of these. And that's how it'll work. So hopefully that makes sense essentially. It's like a modified BFS where you put things that are distance 0 in the front. And this only works, like I said, because these edges are weight 0. So you have to recognize like, okay, if I process something, then I should process everything that's connected to before doing any bricks. And so you can actually do this without jigsters, and then you basically get mn runtime and mn space. So let's take a look at the code for that one. So essentially, standard stuff. You have the directions, the visited, the BFS, all that normal stuff. I did mention earlier that you can use this trick where, to make this a little bit faster, where you mark things visited as soon as they get into your queue. Because if something's in a BFS queue and it goes in later, regardless of the front or the back, if something's in the front, let's say, and it goes in later in the front, like these are going to be the same distance, so you don't need to have it twice. And if something's in the back and it goes in the back, then this is going to be bigger distance or the same, so you don't need to have it twice either. So for BFS, whenever something's in your queue, whenever you put something in your queue, you can just mark it visited right away. So that's kind of what I do here. So we put 0 in our queue, 0, 0, we mark it visited. We get our cell, we get our distance xy, we check, are we at the right place? If we are, just return. Then through all the children, we get our new distance, and we check, like, are we in bounds and have we not been here before? If that's the case, if it's not the case, we'll continue. Otherwise, we mark it visited right away because we don't need to have it in our queue twice. So having something visited or in our queue should be visited. And then we just check. If it's 0, then we add it to the front. If it's non-zero, we add it to the back. And yeah, that's basically all there is. And then I just have this, but this will basically never be hit because there's always a solution. You can just remove a brick if you want to. And yeah, so I did this with jigsters the first time. So this is actually going to be n, where n is the whole grid, and then space, where n is the whole grid. And so we can look here. Yeah, so I think when I did this with jigsters originally, I can show submissions. It was a lot slower, right? Makes sense. And I think that's the more intuitive one, and then this like modified BFS is a little bit less intuitive. But either way, because you can do it with jigsters in roughly the same runtime, it shouldn't be a hard problem for sure. Like, I think the only way it can be a hard problem is if you have to do this BFS or the jigster just fails. So you have to have like tougher constraints or something like that. But yeah, that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.